As a third topic, let's consider asymmetric loading. So before talking about asymmetric loading, let's review what symmetric bending was. So in symmetric bonding, this is the situation we considered. So here we have a member with symmetric cross section, and the way we apply couple of moment couple on left and right side is as follows. If we use the right arrow notation, what you can see here is the torque vector m is parallel to axis z. Okay, so in this case m vector was parallel to z axis. Okay, so for symmetric member, for symmetric bending case, plane of symmetry, which is xy plane, and plane of couple, yeah, this means the couple means like m couple, and this is the plane perpendicular to m vector couple, which is this couple, so which is this plane. So plane of couple and plane of symmetry is equal to each other. Okay, in other words, m is parallel to neutral plane. However, for axial asymmetry case, let's consider the case. Okay, so the question I will ask is, what if the plane of symmetry and plane of couple is not equal to each other? Yeah, it means that member does not bend in the plane of couple. Okay, so even though, yeah, we apply the g in this direction, instead of bending along this xy plane, what you can see is it bends in different direction, so that for this asymmetric loading cases, neutral plane where the normal strain is zero plane, then what you can expect is the this plane and m plane does not correspond to each other. Okay, so this is the special case when m is not parallel to neutral plane, and we call that as asymmetric loading. So after considering these examples, we can ask this question, like, under what condition is m parallel to neutral plane? If we figure out this condition, the condition that m is parallel to neutral plane, then we can also figure out the condition that m is not parallel to neutral plane. So for answer this question, let's consider this continuous system. We're gonna consider m the direction of m as g-axis, and we'll assume all other reactions n, v, t are 0. Okay, so given m applied along g direction, let's try to find this condition, the condition that m is parallel to neutral plane. Okay, so when m is parallel to neutral plane, this is what we can expect. When m is parallel to neutral plane, what you can expect is that the g component of m, which is the m we consider the m we considered in previous sections on symmetric bending, yeah, mg can be written as y times minus dfx. Okay, so mg is the moment m along that direction. This is mg component. If you consider mg component, which is this direction, this kind of torque, then what you can see here is infinitesimal mg from this infinitesimal area is minus dfx multiplied by y. Okay, y minus, because we are considering mg vector in this way, so the torque in that direction and the force, they have different the torque due to this df generates negative torque. Okay, negative mg component. That's why we have to write down infinitesimal mg as minus dfx multiplied by y. In the similar way, infinitesimal dmy can be written as, this is the my component, and my component can be written as g times infinitesimal my, due to this m is dfx multiplied by g. Okay, so please see that my considers this direction of rotation and torque, and infinitesimal dfx generate positive sign of my. Okay, that's why we put gdfx for infinitesimal dmy, and we put negative sign for dmg. Okay, so when m is parallel to neutral plane or neutral plane is parallel to g, what you can expect is the y component of m must be 0, g component of m must be same as the applied moment m. Okay, and the force, if we consider fx, the overall force for entire plane, it must be 0 because n equals to be 0. Okay, so these are the conditions that we can satisfy. Now when m is parallel to neutral plane, we have expression for sigma x, and sigma x can be written as minus y over c multiplied by maximum stress. And if you multiply this expression here, what you can end up is my, which must be 0 when m is parallel to neutral plane. Then it can be written as some constant multiplied by integral yg dA. Okay, so this is how we simplify the integral, and this is condition to have when y component equals to be 0. Integral y multiplied by z dA must be 0 for integral over entire cross section. Okay, so we call this integral as iyz component, and we call coordinate system satisfying iyz equals to be 0 as principal axis. Okay, so let's consider like a geometrical meaning of a principal axis. Regarding like obtaining this principal axis from arbitrary axis, you need a linear algebra knowledge and the eigenvalue and eigenvector analysis. We're gonna skip that, but even though we're not gonna discuss about eigenvalue and eigenvector, I can explain you the concept of a principal axis based on geometrical consideration. Here we're going to consider exactly same cross section. So in the example in the left, we take y prime and g prime axis in that direction. This is 90 degree. In the figure on the right, we take y and g axis in this direction. This is rather conventional. So when we take y prime and g prime axis, let's think about this integral, if this integral will be 0 or not. So if you consider 1 and 3 region, which is quite large region here, what you can see here is you have the sine of y prime is positive and sine of g prime is negative. Okay, so we can expect that for both 3 and 1, when the sine of y prime and g prime is opposite to each other, y prime g prime will have negative values. Okay, now for area 2 and area 4, region 2 and region 4, you can expect that both y and g are positive, or both y prime and g are negative, so that y prime g prime is larger than 0. However, the area for 1 and 3 is much larger than area for 2 and 4 with positive sign. You can expect that, okay, integral y prime g prime should be smaller than 0. Okay, so here the conclusion we can have is y prime and g prime are not principal axis. Now let's consider YZ axis that look like this. Here region 1 and region 3, we have negative an opposite sign of y and z, so positive y and negative g. Here you have negative y and positive g. So for 1 and 3 region, we have negative yg multiplication. For region 2 and 4, we have positive yg. Here y larger than 0, g larger than 0, y smaller than 0, g smaller than 0. So you have a positive sign of yg. So if you do integration for yg dA, you can see that they're gonna cancel out due to their symmetric arrangement, and you can conclude that y and g are principal axis. Hence, if we apply m along the y-axis, if you apply m along that axis, or if you apply m along z-axis, you can expect that m will be on neutral plane. Otherwise, if m is not applied on either y or z, you can expect that m will not be on neutral plane. Okay, so with that, let me finish my third recording about of today's lecture. Okay.